All right, so we're back. We're back here, and as you can see, the scope is gone. Now the scope doesn't have to go. Obviously, you could do the scope at the same time, but for now, the scope is gone. And in its place, we've got computer, and the signal gen is gone. And in its place, what we have is we've got a little USB interface here. And so this is fairly inexpensive, and you probably already have a laptop of some kind or a computer or something like that, and a digital multimeter. So the cool thing about this setup is that you probably already have a lot of this stuff at your fingertips. And this piece of software, there's a free version, and I'm using the free version. So you can totally get it done with the free version of this software. And there are probably other pieces of software that are good as well. This is one I like. It's called REW, which actually stands for Room EQ Wizard. And so this is primarily a piece of software for measuring room acoustics with a microphone. But as it turns out, it actually works just as well, or maybe even better, with measuring devices. And so the first thing you want to do is to get your software open and your device plugged in, and then you just go to your preferences, and you just output device, you select your USB interface, and input device, you select your USB interface. And so we're going to be generating and measuring from the same device here, which in this case is a Scarlett Solo. It's a Focusrite product, and it's great. So the first thing you want to do is measure your loop back to make sure that everything's cool. You just don't have any sort of distortion that you don't know about. Just make sure that the loop back looks good. In this case, I've already done that. Basically, with a loop back, you just run the output straight back into the input with a short cable and just measure the device itself. And this device measures 120 plus signal and noise and distortion of 0.00 something or other. And so it's more than up to the task of measuring this amplifier. And so next thing to do is to pull up the generator. So here's our gen right here. And we can start generating a tone. And so I've got the multimeter hooked up here so we can see like what our power level is that we're generating here. And I'm going to turn this right on down because I've already set this up to be a certain power level. So let's see. So there, negative 16 dB, we're at almost exactly 1 watt because once again, we're measuring into the 4 ohm load here. So we've got 2 volts RMS into our 4 ohm load, which is 1 watt output. And you can also see that our input indicator has lit up here green to show that we have signal coming in. Another thing you need to do, I should have mentioned this before, is that the input on a device like this is not designed to measure the output of an amplifier like this. Usually the output will clip the input before you reach the maximum power of the amplifier. And so what I've done here is I've taken a simple pair of resistors here. I think I have the actual values are not that meaningful as long as they're high enough that they don't load down the amplifier and low enough that they don't create such a large output impedance from the circuit that they mess with this. So anyway, I'm using I think a 10K and a 1K, right? And so I've got the amplifier hooked up across the 10K as well as the load, of course. I've got them hooked up across the 10K and the 1K. But then I have the measurement device connected between the 1K and the ground. So that means it's like a 11 to 1 or whatever ratio that it's being taken down at. That will allow us to run the amplifier up to its maximum power while not overloading the voltage input of the device. And your device's voltage input may vary what it's asking for, right? And so now that we've done this, we can actually pull up the FFT. Now, here's another thing I should mention. This is not a replacement for an oscilloscope. And the reason why is because, I don't know if you remember the last video, but in the last video we noticed that our amplifier oscillates. It oscillates at some large frequency, 200 kilohertz or something like that. And it rings up there, something at the same frequency it oscillates at, it rings at way up there in the hundreds of kilohertz range. This device is only going to measure up to 40K or so, okay? And so, although this is going to give us amazing measurements in the audio range, all those distortions that we were getting from those oscillations, we're not going to see any of that here. And so, if all we had was this setup, we would never know that this amplifier has oscillation and ringing problems. And that's fine. It's just different tools for different things. So anyway, we're generating here, we're receiving here. We know from our multimeter we're getting 1 watt into our 4 ohm load, right? And so now what we can do is we can pull up the RTA. So this comes with an FFT in the software right here. So let's hit record. And there you go. Have a look at this. So here's our noise floor, right? Here's our fundamental. And look, it's already, if you hit the distortion panel, it'll actually give you your total distortion. It'll even number out your harmonic series here. See that? Look here, actually up here in almost 30K, we've got a little bit of some kind of a noise. That may actually be the switching frequency of my power supply. So that may be switching noise coming through there above the audio range. So you can see our total distortion here is 0.025 at 1 watt. That's very good. That's at 1K, of course. We're going to be doing sweeps in a minute, but for now we're just looking at the FFT. And look, we've got a little bit of second, and then third, fourth, fifth, sixth, seventh, all the way up to the ninth are all kind of similar level here. And so that's interesting. Second is dominant though here at 1K, right? So that's pretty neato. That's pretty neato. And we could just do this. We could just sit here and bring our level up and down and look at what happens with the distortion here. But there's a better way of doing this. I mean, obviously this is good for some things. Look down here, this is our 60 Hertz. This is probably leaking through the power supply here. A little bit of 60 cycle hum because my laptop is running on battery, so there's no 60 cycle there. Could be the lights, who knows, right? But you can see versus 1 watt, we're here at 60, and this is down here at below -20, right? And so we're still better than 80 dB signal to noise and hum versus 1 watt. That's not bad. That's pretty good. Yeah, I mean, I've seen better, obviously. Most of my amps are a lot better than that, but that's perfectly reasonable. I mean, the noise in your room is going to be like 40 dB probably. So this is all down in the weeds as far as listening goes. All right, so that's looking good. Let's close that out. Now we will turn off. Now let's remember this -16 because -16 is 1 watt for us, right? So we're going to turn this off. See how we're not generating anymore, right? And let's go to measure. Okay. Set your starting frequency. Well, I mean, obviously you set these however you want, but we're going to be starting at 20 Hertz, and we're going to sweep all the way up to 40K. So that's above. The reason you want to sweep above the audible range is that allows you to look at the harmonic distortion for lower frequencies higher up, because obviously second order, for instance, from your fundamental at 10K is going to be 20K, and second order for 20K is going to be 40K. And so this allows you to measure your harmonic distortion higher the higher you go. You can set your length however you want. This will change the measurement somewhat. This just this changes how long you will spend doing each sweep, right? And there's a little bit of like level of detail there that we get into. You can see here's our level. What did we say we needed? -16, I think, is 1 watt for us. And we can check levels here to make sure we're getting good levels in. And we are. So we've got 25 decibels of headroom, and that's good because we're going to be moving up in power as we do these sweeps to see what we do. So let's do our first measurement here. And we're going to do a bunch of measurements, and I'm not going to make you wait to do all of these. So at some point I'll speed up the video so you can see sort of the final groupings of measurements, whatever. So all right, now this is great. This is like a lot of data. So much more data than just, you know, in the first video we were just doing square waves and sine waves, and we had that sort of piddly FFT on the scope itself. But holy cow, look at this. So for any frequency that you want to choose now, you can come down here and look at the exact percentage of harmonic distortion and noise at that frequency. So it's like we just went through every single frequency and did one of those FFTs to it, right? So we have all of this right here to see. And so we know this is 1 watt, so we'll just go down here and we'll say 1 watt, right? And you can do as many measurements as you want. So that's what we're going to do here in a minute. All right, so here, look, this is as you scroll through these, it'll highlight them in yellow, all right? And so here's our fundamental up here. So you can see our amplifier, pretty linear, nice and flat, all the way from 20 all the way up to 20K. A little bit of roll off up here, not much, and the bass looks good. And so here's our second harmonic. You can see it's dominant here. Now you can see the total, so when you add up all of your distortions, you get the total harmonic distortion. And so the black line there is the total. The red line here is our second harmonic, right there. And then right on up, here's third, fourth, fifth. You can scroll through all of them and see what those are contributing to the total harmonic distortion that you're getting, right? Sorry, it's my scope telling me it wants to turn off. And so let's look. So here we are at 1K, at 1 watt. And you can see our harmonic distortion is low, 0.024. Not bad at all, in the mid-range. But look at this. You know, when we were measuring before, we never would have noticed that, like, look, there's this rise in distortion up to the low range here. And at 30, we're at 0.4. And at 20, we're at 0.53. And so if you only had a 1K measurement of this amp, you would think that it was a 0.025% distortion amp. But you'd be measuring it at sort of its most optimal frequency there, where it generates the lowest, and obviously it's rising up here. So at 1 watt, we're already at 0.124, something like that. These are all perfectly fine numbers. These are not high by any means. But you can see that it's sort of interesting things that the amplifier is doing here. So now what I'm going to do is I'm going to run measurements at plus 1 dB all the way up until the amp is clipping. Okay, and as we're doing it, I'm going to take note of the voltages that we're running, and I'm going to type them into the boxes here as I run the measurements. And then at the end of all that, we're going to have a nice series of measurement all the way from 1 watt up until clipping that we'll be able to scroll through, and we're going to be able to see how the distortion responds to power, and the frequency, how it responds to power, all that kind of stuff. We're going to look at that. But I'll probably fast forward the video while I do this because it's going to be boring. All right. All right, so I went through and did all those sweeps, and I marked down the voltages that were recorded as I went up by 1 dB all the way up till past clipping. And then I went through and I just did V squared over R to get power for each one. So for instance, this 2.25 volts squared divided by 4 is 1.3 watts, and so on and so forth all the way up, so we get the wattage as well. So I calculated that. And now we'll be able to see exactly the different distortions for the different power levels of this amplifier. And I know it's probably hard to see the screen here, and so I'm going to export these and then sort of overlay these during this part of the video so you can kind of see what I'm talking about. I'll do that after I sort of get done talking here. All right, so let's just roll through here for starters. Let's just see how we did. So here's 1 watt, 1.3, 1.6, 2 watts, 2.5 watts, 3.2 watts, 4 watts, 5 watts, 6.25 watts, 8 watts, getting up there now. Starting to get a little bit weird here. Let's see. 10 watts, still, I don't know, it still looks pretty good. 12.6, so this is right before we know that it's about to clip. And here we are. Oh, and there we've gone. This is 1 dB over 12.6 watts was 15.4 watts, and you can see distortion's gone a little bit crazy here, and so that indicates that we're visibly clipping if we were to look at the waveform. And here we went 1 decibel more, 17.5 watts. And you can see our distortion is beyond, it's like 6.32 total harmonic distortion here, and it's almost all third here. So, and you can see the third is up here, pretty constant across there, and all these other distortions creeping up as well. And we can also look at these SPLs numbers here. This will be interesting to see. So these should all be 1 dB apart. You can see the top one is not 1 dB because it's at that point in power compression. It can't get any louder. But the rest of these look pretty good. So you can see that our frequency response doesn't change much throughout the power level until it starts to clip, which is good. All right, so you can see our noise floor. Now our signal noise obviously is going to get better and better the louder we get here. So let's go back to our last unclipped one here. And our distortion is still very nice. In fact, interestingly, the percentage of distortion per signal goes down with this amplifier as power increases up until the point that it clips, right? And so let's look down here, for instance, at 30 hertz. And so here we have a total distortion of 0.09 at 30 hertz, but you'll remember 1 watt at 30 hertz was 0.4. So that's a lot of difference there. And so it's interesting. The amplifiers that I build have limited negative feedback, and they have a tendency to have their distortion be lowest at low powers and gradually climb as you approach clipping, whereas this amplifier, which I think is actually more typical of a solid state sort of high loop negative feedback amplifier, has its highest percentage of distortion at its lowest power levels, which can be problematic actually because most of your listening happens at a couple of watts, right? And so to have that also be the point where the distortion is highest could lead to a bad listening experience, potentially. Now, this still isn't high distortion, 0.4%, but if it's this bad at 1 watt, what is it at 1/10 of a watt? And, a lot of listening, actually, a lot of the sounds in your music, those subtle sounds, happen around 1/10 of a watt as well. And so if it continues to go up, we could test that, of course. We could see maybe it's 1% at 30 hertz at 1/10 of a watt. Who knows, right? We could test it. That's the whole point of this, is to show you how to test your own stuff. And so, yeah, what I'll do now is I'll export all of these and line them all up in the video editor here, and so we can see the whole thing run through in good quality, so you can see all the points. And so you can see now, at any power level, at any frequency, I can find out the harmonic distortion, right? So if I want to know what the harmonic distortion at 30 hertz at 10 watts is, I come down here at 10 watts, I come in here to 30 hertz, let me just scroll up a little bit here so you can see the fundamental, and bam, I can see that my total harmonic distortion is 0.08, it's 0.04 second order, it's 0.05 third order, with a little bit of everything else sort of thrown in for good measure. So you can see what a powerful tool this is, and it's it doesn't cost a lot. You might probably have a lot of this at home already. So we're going to stop there for this video, and in the next video I'm going to show you how to measure the output impedance of your amplifier. And that's important because the output impedance determines how your amplifier interacts with the speaker. And in many ways, it's probably a more important measurement of the sound that you're likely to get out of it than even these distortion measurements. So that's it. Thanks for watching.